The very first statement is always given. Alright, we're supposed to solve for f. Two ways students might approach this algebraically. Some students might get rid of this group times 5/9. To get rid of times 5/9, some people will say divide both sides by 5/9, which means multiply both sides times 9/5, the reciprocal. 9/5 times the left side and 9/5 times the right side. The reason we are allowed to do that is the multiplication, or you can say the division, property of equality. So we're trying to isolate the variable f, so we need to get rid of minus 32. We will use the addition property of equality by adding 32 to both sides, which gives us 9/5 c plus 32 on the left, and f minus 32 plus 32. 32's cancel out, so just f on the right. And now we've isolated f, and what gave us a right to go from here to here was we added 32 to both sides of the equation. That is the addition property of equality. So I said that some students would do this a little differently. Some students might have distributed first. That's okay, you can use the distributive property. Then we'll have c equals 5/9 times f, and 5/9 times 32, which is 1/69. Now we can get rid of minus 1/69, because remember we're trying to solve for variable f. So to unbury that or isolate it, we want to get rid of this minus 1/69. We will add 1/69 to both sides, to the left side and to the right side. It's gone. We're trying to solve for f, so the next stage is to get rid of this times 5/9. We will divide by 5/9, which is the same thing as multiplying by the reciprocal 9/5. Oh, I forgot to justify this. We added 1/16/9 to both sides, the addition property of equality. Alright, solving for f, let's multiply both sides times 9/5, and we'll have f equals 9/5 times the left side. So both of these work. The reason we were able to do that was the multiplication property of equality, because we multiplied the right side times 9/5 and the left side times 9/5. These are equivalent. They look a little different, but they're the same. Alright, the table showing the conversion. They gave us all these temperatures in degrees Celsius. We're going to find their equivalent temperatures in degrees Fahrenheit by using this. We'll plug in 0 for C, and then F is equal to 32 degrees Fahrenheit. If we plug a 20 in for C, 20 plus 1/69 times 9/5, and that's all equal to 68 degrees. And when it's 32 degrees Celsius, it's 89.6 degrees Fahrenheit. And when it's 41 degrees Celsius, it's 105.8 degrees Fahrenheit. That's just from plugging these C values into this formula we solved in part A. Alright, part C. Let's see. Use your table to graph the temperatures. Well, we can treat this like an x-axis and a y-axis. Here we go. On this Celsius axis, we go from 0 up to like 40, so we can just say 10 degrees, 20, 30, 40. And for the vertical Fahrenheit axis, we go all the way to 105. So let's say this is 100, 50, 10, 20, 30, 40, 60, 70, 80, 90. Okay. 0.32. 0.32 is right about there. 20 on the Celsius axis, 68 on the Fahrenheit axis. So this is horizontal, and this is vertical. Go 20 to the right and 68 up. 20 to the right and 68 up. 32 to the right, up almost 90 up. 10, 20, 32, almost 90 up. 41 to the right, about 106 up. 10, 20, 30, 41, and about 106 up. So it says, use your table to graph the temperature in degrees Fahrenheit as a function of the temperature in degrees Celsius. Is this a linear function? Boy, it really does appear to be like a straight line, doesn't it? I would say yes. It does appear to be linear. And this concludes this problem. I hope this helped.